Hello. Okay, let's get started. It's definitely the year of Linux on the desktop. So a little bit about me. So I'm the tech lead on the infra compute team at Lyft, and I've spent the last few years there working on Kubernetes and trying to make it a real thing that takes over the entirety of the stack. So quick agenda in terms of what I'm going to cover. First is sort of an overview of Lyft and our scale and what that looks like. Then I'm going to talk about some of the network fundamentals of Kubernetes. Then I'll do a deep dive into our stack. I'll talk about how we use it with Envoy. And then I'll cover some notes about future work that we have planned. Okay, so in terms of Lyft scale, so we have millions of riders per day, more than 30 million riders, more than 2 million drivers, and we're available in all 50 US states, Toronto, and Ottawa. And hopefully you took a Lyft from the airport and or took a Lyft to get to KubeCon. And those requests definitely went through Kubernetes as part of getting here. So in terms of what the scale of Kubernetes looks like at Lyft today, it's sort of divided into three main areas for the section of the company that I'm in. So we have our machine learning workloads. There are a whole bunch of GPUs there, lots of training jobs that we run, Jupyter Notebook support. And in terms of scale, it's about 5,000 plus pods, and 10,000 cores are dedicated to that effort. Flight, I won't go into too much detail on Flight. There are a whole bunch of other talks at KubeCon on Flight, so I encourage you to go see those. But that's our distributed workflow orchestration system. And that's kind of the inverse of the machine learning in terms of scale. It's flip-flopping the number of pods versus the number of cores. They tend to run lots of sidecars on their side. And then the clusters that my team and I spend most of the time focused on are, and that's made up of 100 plus stateless microservices. All of those, so we have redundant clusters that exist on a per availability zone basis. And I'll talk about that more in detail. And all those are part of a single production Envoy mesh. And in terms of like the scale, in terms of the numbers, we use HPAs aggressively. So the number of pods that we have and the number of EC2 instances that we're running greatly varies based on time of the day and load. And we run a whole bunch of sidecars. This talk doesn't get into it, but a lot of the work that we've done has been related to sidecar ordering and making sure that like what a Lyft service developer expects to be the case, like the same for the legacy stack, holds true for the Kubernetes world. So about 100,000 containers plus and 3,000 plus cores for that environment. In terms of the timeline, so in December of 2015, we started an internal Docker-based effort at the time to sort of create a container-based system for handling our development and continuous integration stacks. But all of our production side is basically stateless services running on autoscaling groups and just raw EC2 instances. So it was about May of 2017 when we started investigating options for running Kubernetes on AWS. And at least at the time, we didn't feel that any of the available options could necessarily like work at the scale that we needed for them to, and or were too complicated. And so that was when we kind of went back to first principles and tried to figure out the most performant and the best method for mapping AWS VPC constructs onto Kubernetes and the CNI stack specifically. So we did a whole bunch of dev work, and then in December of 2017 is when we open sourced that stack. It just so happens that the AWS stack, they were doing their development at the same time we were, and so both of us released our stacks at roughly the same time. And then we spent most of 2018 getting all of our batch and ML workloads migrated over to Kubernetes, in addition to sort of doing the plumbing work that we needed to do for the stateless services. I mentioned sidecars. There's a whole bunch of stuff that happened as part of needing to get stateless there. And so this year has been focused mostly on migrating services, or the stateless services that are the core of the platform over to Kubernetes. And that does include tier 0 services. So the tier 0 services are the ones, if that service is down, then Lyft itself is hard down. So in terms of what our production environment looks like today, we're on Kubernetes 114. The plan is to move to 116 by the end of the year. That works starting this week, probably. In terms of the operating system that we use, we tend to hold back one release from the current production Fedora release. So it's very minimal, small OS. We use Cryo as our container runtime environment. So that gives us like a handful of good things in the sense of like, we have kernels that are very close to mainline, lots of bug fixes, they handle containers well, and we use systemd to handle all the secret management. So on the flip side of that is that most of the internal developers at Lyft don't know that we run Fedora as sort of like the bootstrap OS because they just use Ubuntu. And so most of that is based on Bionic. All of our infrastructure is immutable on the Kubernetes side. We build AMIs from Packer. We use Terraform orchestration. We try very much, and there's other talks at KubeCon as well that sort of talk about how we roll the clusters and how we maintain that state. Yeah, so we're almost entirely in AWS. Our largest build out is US East 1. We also have some clusters over in US West 2 as well. As I mentioned before, we have per AZ clusters. So we have separate clusters for staging production. This lets us do staggered rollouts. So we can have a very well-defined process. So if we end up taking a change to, say, a staging cluster, it's likely that we only packed one staging cluster as opposed to all staging clusters. And then in the case of production as well, it's not likely that we have a change rollout that affects all of prod. And then, of course, on top of all this, we run our stack, which I'll talk about. But yeah, it's VPC native, low latency, high throughput, and most importantly, pods are directly part of the Envoy mesh. Okay, so covering some brief like networking 101 for Kubernetes. And these are the requirements that make it, in particularly, pretty difficult to map Kubernetes constructs onto how the AWS VPC was originally created. I'm not sure the year of that date, but it's been around for a long time. It's very stable. So we have one IP per pod. Nodes have to support at least 110 pods, so that's like the minimum of the maximum. They can do more if they want to, but they have to support at least 110, which by that definition, it means that we have to have at least 110 IPs per Kubernetes node. And so then there are a whole bunch of like rules related to NAT about how you basically can't have it. So containers have to talk to other containers without going through NAT. Nodes can talk to containers, et cetera. And then another point, which is also fairly tricky, depending on like how your network is set up, is that the IP that a pod sees itself as has to be the same IP that everyone else sees it as. So you can't have effectively like two identities for the same pod. Okay, so in terms of sort of the network options, and this is sort of almost time-based as well in terms of how CNI plugins sort of developed and what was available. The very most like simplest, very straightforward, which is what I think a lot of people used early on. It's very high performant. Is you just take a /24 per node and you just pull it down to the EC2 instance. So you effectively have around 255 IPs. And you get a max of 50 routes. I'll talk about that in a little bit, or default max of 50 routes. And then the overlay network space is where most CNI plugins, I'd say, operate, or most of the ones that are used in production. And that sort of abstracts away, or tries to abstract away a lot of the underlying network semantics and sort of lets you operate at a higher level. And then you have your VPC native networks, of which the Lyft stack is one of those. Okay, so I'll go into each of these briefly. So we have a /24 per EC2 node as one option. So previously, the limit on this, you could only have 100 routes per VPC back in 2017 when we first started looking at all this, which meant that roughly you had on the order of 100 node cluster was the most you could get out of VPC. Since then, AWS has increased the limits, added an order of magnitude. So now you can have up to 1,000 routes. So you can have a much larger cluster if this is your method of getting IPs down to an EC2 node for Kubernetes to use. Okay, so the next set of options involve overlay networks. These tend to be cloud agnostic. You tend not to have limits on your cluster size. You get just like all these complexities. You have IP and IP. Often you might be managing BGP, and effectively. Can you turn on this mic? Handheld? Yes, good? People hear me? Okay. Okay, sorry about that. Okay, cloud agnostic, no limits on cluster size. Okay, so effectively, like AWS itself and the VPC is a software-defined network that has a very, it's a very good API. It's been around for a long time, but it's very stable and it does what it does. And so effectively, what you're doing if you run an overlay network is you're choosing to run a software-defined network on top of a software-defined network. So you're in this like whole other business, which I don't know that people necessarily want to be in if you're paying AWS to run your network for you. And also because you have these sorts of limitations, you might have issues connecting to the Envoy mesh, you might have to use NAT, and there's just like lots of like hard edges, if you will. I guess one thing is like a lot of these are fairly easy to set up. In terms of just like point and click and get them up and running, but it's like once you have a problem, it can be really complicated to debug what's going on. Okay, so next category, which didn't exist at the time when we started writing all this 2 years ago, were options to talk to the VPC network natively. So all this is, from our view at least, it's very simple and straightforward. There's not a lot of code that exists to make all this work. Pods receive full VPC IP addresses, and they get full connectivity within the VPC. So anything else in the VPC, whether it's an Amazon service or some legacy service you're running that you have, like you just can talk to it, and it's another VPC IP address. And then one of the most important points is that you get native network performance, or you should get like near native network performance. And so the two main options there, the AWS option and also Lyft, and both were developed around the same time. And so my talk covers mostly the Lyft side of things. Okay. Our stack. So it's very minimal. There's no daemon sets, there's pods, there's no runtimes. It's a handful of stateless Go binaries. We run everything in production with Cryo. Datadog runs their production workloads in Containerd. As I mentioned, no overlay. There are two interfaces I'll talk about that live inside of our environment, which is the IP VLAN interface and an unnumbered point-to-point interface. And kind of most importantly is like you don't need to change anything about your VPC. So you don't have to fiddle with like asymmetric routing. You don't have to like change your route table. It's intended to just work however your VPC is currently configured. And from our perspective, it's basically feature complete. We've been running in production for 2 years with very minimal changes. So regarding IP VLAN, if you're not aware of it, there's some good papers about it. There's a lot of talks that have been presented over the years about it. But it was created by Google in 2014. It shipped with Linux 3.18. The primary benefit, it was essentially designed to work with containers, and it avoids going back and forth between the default network namespace or the host namespace. So with a lot of systems for getting IPs into containers or into network namespace within Linux, you've got to effectively have a virtual Ethernet device or like some sort of bridge that sends the packets back and forth through the main namespace. So in our case, we can take AWS Elastic Network Interfaces, which are like our host network adapters, and then tie those directly into pods. So there's very little overhead. I'd argue that at least it's probably the least amount of overhead that you can have in order to get IPs into pods. And then in particular, I don't know if Google like knew this at the time, but IP VLAN maps basically perfectly to the constraints on the AWS VPC design. Particularly, in our case, we're in IP VLAN in layer 2 mode, and that just, it works out really well. Okay, so I mentioned ENIs earlier. It's a virtual NIC. And so the number of ENIs that you can have per EC2 instance is based on the instance size. So right now that's 2 to 15. And then also the number of IPs you can have per ENI also varies based on the instance size. And so the point I mentioned earlier about needing to support up to 110 pods or 110 IPs per node. So if you want like a fully conformant implementation of Kubernetes using the stack, then that means that you have to use, at least for like the modern EC2 instances, you need to use a 4x large or larger. So this is not a system that's appropriate for, say, like, a T2 or a T3 micro. But again, this is more for a production environment, not necessarily for like, a development environment. In terms of how we manage ENIs, that's all managed by the CNI. So we reserve the boot ENI for the Kubernetes control plane, and also any services that need the host IP. And then we effectively pull down ENIs as we need to, and then IP addresses get added to the ENIs until they're full. And then once the ENI is full, we make a new ENI and we add IPs to that. And there's some options to like pre-allocate ENIs on boot if you want to, just to save the overhead from that. By default, we use a 60-second TTL, so those IP addresses get reused as we need to, and that's. But effectively, like in a Kubernetes environment, it's very common to have a lot of pod churn, and so we try to hang on to those IPs when we can and just reuse them. Okay, so if you end up kubectling exec into a pod, you'll see, in addition to loopback interface, you'll see 2 main interfaces. One is ETH0, which is your IP VLAN interface. And so that's the one that's tied directly back to the ENI that you're attached to. All VPC traffic goes out that address. And additionally, it's also isolated from all the other ENIs on the system. And then the other interface that we have, since you're probably going to have traffic that is not directly over the VPC, is we have an unnumbered P2P interface. So this is effectively a high-speed interconnect back to the host namespace. So if you have any pods with host networking, or if you have any kubeproxy virtual IP addresses, any sort of like the networking magic layer that Kubernetes does, all this traffic goes out over v0. And so there's sort of this, I think it's kind of a neat little hack, but it's specified in RFC 5309, which is that if an IP address doesn't exist for an interface, then an IP address gets borrowed. So in our case, this particular interface doesn't have an IP address at all on either side, and it's going to borrow the VPC IP address from ETH0. And so if you recall back when I was talking about how like everyone else has to see you with the same IP as what you see yourself as, that's how we achieve it for this particular interface. And then also this interface gets used for internet egress if that's something that you need to do in your environment, which we do. So how the internet egress works. So this is a feature of EC2 hosts where you can have a private IP of your boot network adapter, which can map to a public IP. And then any traffic that gets sent out, that interface, ends up getting natted by AWS in order to talk to the public internet. And so in our case, because we can like get to the public internet over this interface, and it's redundant and scalable, doesn't involve any sort of like single points of failure, we end up having our pods, we end up source matting for those pods, and so that's how traffic gets out. So it does mean that if you're going to the public internet, then you incur a latency overhead, and then you also have to go through NAT. So the network path there is a bit more complex, whereas if you're on the VPC, it's just direct communications between 2 IPs. And so kind of the takeaway there is that if it's possible, you should use VPC endpoints for your AWS services, because that means that you're going to egress on your VPC interface over IP VLAN, as opposed to going out through the NAT side. Okay, some notes about us running Envoy in production. Okay, so this is kind of a rough diagram of what it looks like for our production network. So we have 5 core clusters that are each per AZ. We also have a staging environment that looks similar to this. And then we have the legacy stack as well. And so, as I mentioned before, it lets us like incrementally roll out, and it also means that if we lose a whole entire cluster, then Lyft as a whole stays up. So services end up deploying to all of the core clusters, and HPAs run on each of those clusters to scale services up and down. Okay, so pods are made up of a whole bunch of containers. I'm not going to go too much in detail about this. Kind of the important thing is that we have the Lyft service, which is Python, Go, or JavaScript. Most of our services are in Python or Go. And then we have an Envoy sidecar. But there are a handful of other sidecars that include runtime changes, logging stats, and business metrics, sort of what you'd expect. And a lot of what we've done for a production environment has been related to orchestrating how these containers come up and shut down. Okay, for the Lyft Envoy control plane, as I've mentioned like a million times, all pods have a VPC IP address. And so in particular, one of the cool aspects of this in terms of how we were like initially rolling this out and how it could be incremental is that the earlier versions of Envoy and our control plane could not tell the difference whether or not a service was running in Kubernetes or was running on our legacy stack just using EC2 instances with auto-scaling groups. So from Envoy's perspective, it has an IP, and that just becomes part of the mesh. So it health checks it, like everything that you'd expect would work. So we had a controller that was on all of our core clusters, and that would watch for pods to come up, and then register those into our open source service discovery layer. And so since then, we've revamped the control plane. Envoy Manager is what it's called today. But Envoy Manager itself uses informers to determine pod status, and it connects to all the core clusters. And that's how all the different Kubernetes clusters get bridged together into a single mesh. So in terms of so I mentioned before about the pods, and we have like all these sidecar containers. So one of those containers is the Envoy Mesh sidecar. And so those need to get XDS data as part of their startup. In order to do that, we run a headless service for Envoy Manager. And so effectively all the Envoy managers that are in a Kubernetes cluster, it just has a list of all their IP addresses, which again are VPC IPs, nothing special about them. And then the Envoy sidecar can use DNS to bootstrap itself and get up and running. Okay, some of the migration takeaways or things that we've learned throughout this like 2-year process. So having this ability to do hybrid deployments has been a huge win. In particular, we can have these services that are on ASGs, on EC2 instances that are scaling up and down. And like while that is still running, we can deploy a Kubernetes version of their service on HPAs, and that can scale as well. And so basically, we can like incrementally decrease the size of the ASG, and then let the HPA handle more and more of the work. Where it eventually, like everything gets migrated, and that service gets turned off, and we delete the ASG on the legacy side. And I think kind of one of the other sort of like driving factor for us in terms of design is to avoid complexity on the network. I think Kubernetes as a whole lets you. There's a lot of magic there, which I think is great for development environments, and is also good for sort of like setting up things quickly or maybe like smaller production environments. But if you have Envoy up and running and you have a production network, you want to try to avoid any technology you don't absolutely need. And so if you need a technology, please feel free to use it. But I guess it's important to understand the complexity and what it's doing behind the scenes to make that happen. Because if it breaks, it's going to be that much harder to debug, because at that point, you're going to have to understand how all the magic works. And then in terms of IP VLAN, it's worked really well for us. We keep latency stats, or latency numbers for all of our Lyft services. That's all exported as part of the Envoy metrics. P95 and P99 has been same across this. So in that sense, from a network perspective, the migration has been very transparent for service owners at Lyft. I think also another sort of important item is that the VPC continues to work as intended. It means that if you are seeing a problem with the VPC, it means you can file a ticket with AWS and ask them what's going on. And it's not like this convoluted setup with like IP and IP, or you're not sure where the performance issue is or what's going on. But effectively, you end up with the same performance and throughput as you would expect without using this setup. The other thing is if you have a way to get your tier 0 services onto multiple clusters, I would say do that. I think one of my fears, or kept me up a lot at night, was like, okay, well, if we lose a cluster, does Lyft go down? And so it's very important to me that we can lose a cluster. The goal is to not lose a cluster. But if we do lose a production cluster, it's no different than losing an availability zone. So AZs go away from time to time. Sometimes they blip or brown out. But overall, the Envoy mesh should be able to deal with that. And you should be able to scale into other AZs that are healthy. And so far, this setup has been working well for us. In terms of future work, so we're not looking to add any significant features to the code base. So again, 2 years, minimal changes. If there's something that we feel would be useful, we're happy to add it. But in general, we feel that it's fairly done. We don't use IPv6 internally. Maybe one day we will. When that day happens, we'll write the code for IPv6. If anyone else wants to add that, we're more than welcome to set patches for that. And one particular take as well, which I think was like a lot of discussion early on, is how to handle network policies. And I think CNI chaining is probably the correct approach there, and that you have a specific stack that is not your core stack, which is responsible for handling network policy enforcement. So in general, it looks like Cilium should be pretty easy to wire up with our stack, so we're looking up into doing that with their CNI chaining. Another thing that's currently under development is using traffic control to restrict bandwidth based on CPU count. So this isn't really a production issue for us right now, or has not been, just because of how large the instances that we run. And so when we're scheduling pods against nodes, we run out of CPU and memory like way before we end up running out of network bandwidth. So a whole bunch of thank yous. Main contributors are Lyft and Datadog to the stack, but there have been a handful of other people that have also contributed to the GitHub project. So thanks very much. Very last happy hour tonight, 7 to 10 p.m. Feel free to come hang out. Any questions?
Just a reminder before folks leave, if you can rate this session and other sessions you attend on the schedule, it really helps us with planning future KubeCons.
Can you speak a bit about what the difference between the Lyft one is and the AWS VPC CNI?
They're similar. I don't want to speak too much in detail about that. I'd rather have AWS talk about that. Ours uses IPVLAN. They currently don't use that. I think I'd argue that our stack is simpler and does less, but it intentionally does less.
How do you manage the IP address? Because typically Amazon VPC gives /16, but with containers, you have 100K containers. Do you reuse the IP addresses, or how do you manage the IP addresses?
Yeah, so you effectively tag what subnets you want to use within that. And our plugin will burn down IP addresses at an equal rate. So whatever subnets are allowed for it to use, it'll make sure that those get burned down evenly. And then additionally, you can have secondary CIDRs on your VPC, which I think AWS introduced within the past couple of years. But it's you can add more /16s to your VPC, and you can assign those to clusters. So like effectively, there's a lot of runway for v4 address space within a single VPC.
Hi. I like the per AZ kind of cluster concept. Could you talk just a little bit about the failover mechanism and how that works?
It's Envoy.
Okay.
Yeah. So it's an Envoy mesh. If services start to degrade in one cluster, then they'll scale up in another cluster.
So what was the actual latency impact? Like, how much does it lower it? Does it matter?
Negligible. And we actually, internally, we don't have really good stats on like P999. So there's probably some like differences on like P999. But there's a handful of papers out there that cover IP VLAN latencies and performance testing. But in our practice for what we care about, which is P99, it's been equivalent.
Hi. Do you have any figures to support that it has low latency and you were able to achieve low latency?
Internal data from our Envoy mesh. I'm happy to point you to like other papers that talk about IP VLAN latency.
Okay.
Hi. With multiple clusters, how do you keep them in sync as far as what's provisioned, the versions of the applications, etc.?
So we have a very sort of like lightweight, I'd say it's sort of like, I won't call it federation, but it's a very lightweight stack that merges together all the clusters, and that if you're a Lyft developer or if you're using a deployment stack, you end up deploying to all the clusters. And so as part of the deploy, you can determine whether or not your application failed deploying to a particular cluster. But each cluster is treated independently.
Hi, thank you for the talk. Has any attempt been made to get Lyft CNI working with other cloud providers like GCP?
No, in this case, like it is, again, there's not a lot of code there, and it's heavily dependent upon AWS APIs. So it's very much dependent on the VPC. Okay. So yeah, it wouldn't be appropriate for a different cloud provider.
Thanks.
I mean, having said that, I would say that regardless of what cloud provider you're using, for production, you want something that gives you this like one-to-one mapping of a VPC IP address to a pod IP. Like you want it to be as simple as possible. In our case, it's for the Amazon stack.
Are you using the AWS security construct, like security groups for the communication between your containers?
Yes. There are some caveats there in terms of how we handle ENI and security groups. I can talk with you about it offline.
Okay, thank you.
Hi, thanks for a great talk. I wasn't quite clear on how you got between regions. If I understand correctly, AWS VPCs don't span between regions, and your...
Correct, they don't.
So how do you bridge that gap? Did I miss something?
No, we run predominantly in US East 1. So it kind of determines on what the service is and what the application is. But in this sense, this particular design and setup is for a single region.
Okay, so you're saying you don't span regions at all, or you do sometimes, and you're not telling us how you do it, or?
Those are separate meshes.
Okay.
Yeah, so separate environments. Yeah.
Okay, gotcha.
Yep.
All right, we have time for one more.
I just want to reconfirm in terms of where do you apply the security policies for the containers? Like the containers are accessible outside to the internet, or do you apply the policies that this container has to talk outside, this container does not have to?
The security groups are on a per ENI basis. And so fundamentally, whatever ENIs you have set up for which cluster, that determines who can talk to who at the AWS level. So our pods are not addressable from the public internet. So there is a way for our pods to egress to the public internet over NAT, but that doesn't mean that someone from the public internet can access those pods.
All right, thank you everyone for attending.